So today what we're going to do is we're going to begin an introduction to calculus where we're not going to talk much calculus, but we're going to back up a bit and talk a little bit about what calculus is and what it does. And you can kind of think of calculus as the mathematics of change, okay? Because if you think about, we looked at some changes when we had some linear equations, straight lines, right? And when we had some curves, we had some parabolas, okay? And we had some other types of curves. We did some cubics when we did the algebra section, right? So we have change, and calculus is the mathematics that describes that change. It describes what's happening. So in mathematics, change, when you think about when a line is going up, what do we call that movement up? It's called the slope, right? So calculus is just a way of finding the slope when you don't have a nice straight line or a parabola. You have some other function that does wild and crazy things and you want to find the slope at a particular point. Okay? So calculus is just defined as the mathematics of change. In order to understand that, we need to talk a little bit about gradient or slope and just a review of some of that information. So that's what we're going to do today as we introduce the calculus. And then we might be able to talk about the first part of it, but we'll see where we get. Okay? So if you look in your books on page 6, the first thing that we talked about it was we're going to talk the idea of slope. Remember, slope is always represented by the little letter m, right? And it's measured as rise over what? Run. Remember, if you're able to count it. But of course, in many of these functions that we're going to be working with, it's wavy and they're going everywhere, or there's a lot of change depending on what's happening, and so there aren't slopes. But just a couple of things though. If you have a line and it's going like this, we say that line, because we always read them from left to right, that line is going up. So what do we know about the slope, about the sign of it? It's positive. Going down like this, we would say the slope is negative. Good. What if it was flat? The slope is 0. There's no change, right? We often call that constant. Yeah? Right? It's not changing anymore, so we call it constant. Remember that? Yeah. Okay, good. Now, what if you have a line that's going straight up and down? Do you remember that one? That's a special case. The slope is undefined. Remember, we can't measure that as rise over run, because it rises all there is, but it runs none, right? Which puts a zero in the denominator, but that makes the whole thing undefined. Okay? All right. Then we talked, if you turn the page to page 8, we talked about the slopes of a parabola, right? And because a parabola is a curve, the slope is measured at certain points to see what the slope is doing. Because remember that at some points a parabola is going down, which means slope is what? Negative. Some points a parabola is going up, which means the slope is what? Positive, right? Okay. Right. So in that case, you can't really measure the slope as just one particular number. It's going to change as you move. Okay? And at that very top point or bottom point, remember the turning point. So in this case, m is it's going down, so the slope is what? Negative. Here, it's right at that point, just at that tiniest little point where the curve, where it stops going down and starts going up, the slope is 0. Now it's not a big space. It's just one tiny little point, and then as it starts going up again, the slope becomes what? Positive. Okay. Now notice that it gets wider as it goes out, which means that the slope is changing as you move. So depending on where you are, you're going to get different slopes. Yeah? Okay. And we're going to look a lot at the relationships between between these and linear functions. Okay? Right? And then finally on page 10 you see the example of a cubic, and again you have that means a line. Remember that cubics are those shapes that go like this, where it goes up and then down, or it can go the opposite direction, right? Right at where the curve points, that's where the slope is 0.
What is the definition of cubic?
A cubic, it's a function that's to the third power. So like y equals x to the third, right? They're always named by the highest exponent in them, and a degree of 3 is a cube. Yeah. So here the slope is also 0. Here the slope it's going up, so that means the slope is positive. Here it starts going down. Then here it starts going up again. So you see that it has a specific behavior. If you reverse the slope, reverse the cubic to go the other direction, you'll be doing just the opposite things, right? Okay? All right. Sounds good? Now, don't worry about sketching those things. We're not going to worry about that. But instead, go to page 13 and look at Calculus, the Mathematics of Change. I didn't even read that before I wrote that. I'm such a genius. All right. So, page 13, yes. Okay? So you can see lots of different measures of change and how they are affected. So reading the graph. Remember that the graph has an x-axis on the bottom, right? The horizontal axis is the x-axis. That's known as the independent variable. It can be anything. And then the y-axis is determined by, for example, like in this one, it's time. As time goes by, the plane climbs what? Higher. Yeah, it's going up. You betcha. Okay? And how high it is depends on how long it's been flying. Does that make sense? And so that's why time is the independent variable. It can be anything. And the height or the y value is the dependent variable, because the height is going to depend on how long you've been in the air. Okay? So look at something like number 2, the trajectory of a ball thrown up from a balcony until it lands off the ground. It's thrown. Notice it starts at 2. Why does it start up at 2?
Because
2 meters.
it would be like thrown.
Because you're on a balcony when you throw it, yeah. Where would it be if you threw it from the ground?
0.
If you were laying on the ground, it'd probably be closer to 1 meter if you were right. So be careful.
And whether you throw it from down there.
Yeah. If it was on the ground when it started.
You could see the ground and then like flip.
Exactly. But that's a huge point, and it's a huge issue for students, because that knowing where it started makes a huge difference to you, okay? So, did it start where you were already 2 meters? Did you throw the ball? If you did, that probably means it was about 1 meter high, right? When you started or so, or a little more. Or were you launching a rocket off the ground, which means it starts at what? 0 on the ground, right? So keep that in mind, hugely important. And you can measure the change in those, and that's what we're going to use calculus for. Now, I want to talk a little bit about some notation. So look on page 14 for some notation. Page 14. Come on, guys. All right. And I want to tell you that I do not count off for this notation. In my world, in my mind, they are completely interchangeable. That does not mean that on your external, your grader may feel that way, though.
It's like if it's in that formula, you have to.
Yes. So, for example, if you're given a y equals function, in other words, it just says y equals some polynomial or some function, then when you do the differentiation for these, you're going to label the differentiation as dy over dx. And what that literally means is the change in y with respect to x. You do not have to quote that. You do not have to memorize that. But if you start off with a y function, then dy dx is the proper notation.
Wait, so it's the change in...
It's the change in y over the change in x's. Rise over run, in other words. Right? Okay, do you see that? All right, and the D comes from the Greek letter delta, which is used to which Leibniz, the German guy who invented two people invented it at the same time.
And then there was this beef over whose one's better. So
Yeah, I'm a Leibniz kind of guy myself, but anyway, there's a Newton. Anyway, and then the other one, if it's given to you, guys, come on, if it's given to you in functional notation, then all you need to do is write f prime of x. That little apostrophe is read as prime. Now you will see that almost always I use that notation.
Wait, what is the first one called?
Okay?
Say?
It's
Does that start
the derivative of y in respect to the derivative of x. dy dx is what, you just call it dy dx. It's fine. Okay? Now, I almost always use this one because in reality, y is the same thing as saying f of x, and f of x is the same thing as saying what? Y. Okay? So if one of you will remind me, I will check to see what the external graders do. I'm always a little nervous about NCEA external graders, you know? Okay?
What would you write if you had to write a sentence about the F one?
There wouldn't be just the derivative of f of x is f prime of x. So that little symbol just means you took the derivative. Okay? Now, we've been talking about derivative, but we really don't know what that means yet, but we'll talk about derivative and how to find it. Most of you have seen a derivative or talked about derivative. Okay? All right? So those are the two notations. And again, in my mind, it doesn't make a darn bit of difference, but it might when someone else is grading it again. If one of you will remind me, I'll check with Mr. Kavanaugh or one of the others to find out. Okay? All right. The book uses both notations, so I would too. Okay?